just like that's like lesson number one. Do you want to have a career? Show up on time.
Right, right. Oh, I meant just sense of time, like knowing how long
No, I
things
know.
take. Right,
I know.
yeah. No, that's true. That's true. Uh, yeah, one time, one of my old, one of the first jobbing things I did way back, and the band leader said, like, I think I'm going to open up a conservatory. It's going to be called a Conservatory of Time. Are you telling me something?
Right.
What's your original instrument? I know
Well, that's a
you
good
were
question.
programming first.
Yeah, I mean, I didn't really get into music until I was 18, so I started studying piano and voice.
Uh,
I'm not good at either of those. I can do a mean Elvis impersonation, and that's about all I got at this point. So,
that's good.
at least I have that.
I shouldn't say it because but I did see him when I was really really young.
Awesome.
Yeah, in
Okay.
Vegas.
Okay, you got 1 minute to showtime.
All right,
One more minute.
how are we doing
All
on
right.
bodies?
Oh, I think
Uh,
this may be better
I
than
see
microphone.
36. I see 36 participants.
Yeah, Vijay, you're better.
Yeah.
Yeah, that's good
And
now.
much better now. Much better. Very good.
It's on the Zoom. In the Zoom setting, you need to select the microphone.
That is true.
Yeah, it's not, Zoom is not always
Oh,
the
they're
easiest
piling
to
in
figure
now.
out.
And you said that um,
Okay. All right, so everybody here online? Yes, so we're here at 6 o'clock Chicago time. So welcome everyone to our ACM Chicago October edition of our webinar. So thank you very much for all of you that are joining. We also would like to also thank as well, this is also being co-sponsored with IEEE Computer Society of Chicago. So we thank those members that are here tonight, and also as well with the Mid-America IT.
Hi everyone. This is we had a little technical problem. We're going to be getting ready our presentation
A little
soon.
bit different.
Oh, there's Alvin.
what
Okay,
we've done.
good.
Yeah, so something that we have a little bit different that we've done in the past. So it's called Software Musical Instrument Design with Machine Learning and Machine Listening. And we have Professor Sam Pluta, who's the Assistant Professor of Music from University of Chicago that will be speaking. But before we do that, just a little bit about ACM Chicago. So for those people who don't know, so ACM is the Association for Computing Machinery. So it's a computer professional organization, and we are the Chicago chapter of ACM. And we hold monthly meetings on topics that deal with computing, like the ones here tonight. So I am the chair. So I'm Alvin Chin. You can mail me at chair@chicagoacm.org. My day job is working for BMW as a senior machine learning researcher. We have our vice chair, Mark Temkin, who will be the one that will be introducing our speaker tonight. We have our treasurer, Greg Newmark. Our web is chicagoacm.org. And I'm sure a lot of you people here know about this meetup from our meetup page. We also on social media, so you can also follow us, like us, connect with us on Facebook, Twitter, and LinkedIn. So these slides will be made available, so you don't have to worry about having to jot this down. Also as well, we'd like to present, welcome IEEE Computer Society Chicago members too as well. So IEEE is kind of like a sister organization of ACM, kind of a similar to as well, but different organization. So I am the chair of that organization as well. We have our vice chair, Gina Martinez, and we do deal with topics that are very similar to ACM. So we've been doing, during this COVID pandemic, we've been doing lots of joint webinars together that benefit both our organizations. And again, here is the web, Facebook, Twitter, and LinkedIn if you want to know more about us. And then I'm going to turn it to Vijay, who will be talking about the Mid-America IT Connect. So Vijay, go ahead and
Thanks, Alvin. Good evening, everyone. Mid-America IT Connect is, thank you for giving the opportunity to co-host this event, Alvin, and along with the ACM Chicago and IEEE. My name is Vijay Konkimala. I'm the founder of the Mid-America IT Connect. Mid-America IT Connect was started about 3.5 years ago to share and collaborate on cutting-edge technology. And Mid-America IT Connect is a private club in Chicago with beautiful panoramic views. I should definitely visit when you get a chance. And this event is our 36th presentation. And we are very excited to have Mr. Sam Pluta, who's the assistant professor of music at University of Chicago, to hear the talk about the software musical instrument design, machine learning, and machine listening. Please welcome Mr. Sam Pluta. Over to you, Alvin.
Okay, thank you. All right, so
Tonight's guest, Sam Pluta, is in the rare group of musicians who perform, compose, is an improviser, and on top of that is an instrument builder of software musical instruments. Sam has composed and performed with the top ensembles in contemporary music, including the Wet Ink Ensemble, the International Contemporary Ensemble, and had his works performed by the New York Philharmonic. At the ACM, we pick up presentation ideas anywhere. I first learned about Sam from the online sessions of the Grammy-nominated Spectral Quartet, a string quartet that performs works from 300 years ago to now, from Beethoven to Philip Glass. From that introduction, I listened to Sam's electroacoustic works and learned about his musical influences. Given that, I knew he would be a great presenter for the ACM. To get his unique view of software musical instrument design with machine learning and machine listening, let's welcome our Chicago ACM guest, Sam Pluta.
all right then. Thank you very much, Mark, for that beautiful introduction. Okay, so Sam, the floor is yours.
All right. Well, first of all, thank you all for having me, and a special thank to Mark, Vijay, and Alvin, all the people in the ACM Chicago and IEEE. There's a couple things there that Mark mentioned in his introduction, that he saw me in this Spectral Quartet presentation, or talking with Spectral Quartet on a string quartet, which was completely acoustic piece, so totally written for acoustic instruments. But what I'm going to talk about tonight is kind of not the opposite of that, because that string quartet, which you should check out their new recording, it's really fantastic. That string quartet is a piece that I wrote for instruments that I'm trying to write down what I'm actually doing when I'm using my electronic instrument. So tonight we're going to talk about my electronic instrument. There's a whole set of stuff that that I'm not going to probably get to about like how the whole instrument works, but I want to like focus in on elements of machine learning and machine listening that I've been exploring in the last year or 2 years. So I think the best way to start. Oh, and just just to say, machine learning and listening in computer music has been happening for 20 years. But in the last couple of years, and we see this in probably a lot of you are using far more advanced technologies than I'm using. But what we've seen is the ability to use this in a live setting. And I think that's the thing that's super exciting, is like using it in a live setting and getting into a feedback loop with the technology. And hopefully that's what I can get across tonight. So I'm going to bring up a little video. So I'm going to start with so there's my talk. Hopefully you all can hear this when I press play. And if you can't, then just stop me. But we tested it and you could hear it. We could hear it before. So, so this is just a video I made yesterday of me playing. And just notice that in the middle here, there is iPad. On the left, there's an iPad. So 2 iPads and joystick right here. And the joystick and this, hey Alvin, can you see my my cursor or no?
I don't see your screen being shared.
You don't see my screen being shared. Well, that's good to know. Yes. Sorry about that. Didn't press the button. Now, do you see my screen being shared?
Yes, we do. Thank you.
Okay, great. Okay, so now when you see this, can you see my cursor? No, probably not.
Yes, we can.
Oh, you can. Okay, great. So I have a joystick right here on the right. Just traditional like flight simulator joystick, and this joystick has an X, Y, and a yaw. So it goes left, right, and I'm sure there's a lot of gamers here. Up, down, and then yaw, so it twists to the left and twists to the right. So it gives 3 values, and then right here and on this iPad, I have 2 pads. 2 XY pads. So here we have XY and XY, so that has 4 values. So these are the two controllers that are controlling the neural networks, and so the rest of the instrument is all this other stuff over here on the left iPad. But most of the neural network stuff is on the right iPad and in this joystick. So that's just to know what to look for what I'm doing. And I'll press play, and then I'll talk about it. Okay, so hopefully you heard that. Hopefully you're still there. All I can see is my own screen. So the what I'm going to talk about here is the instrument, one of the instruments that I'm playing with the joystick and then with the XY controller. So the synthesis technique that I'm using in this is called cross-feedback synthesis. And on a Eurorack, if anyone's played around with the Euroracks, these are like so addictive and fun. And if you're into technology and music and you have money to dump into a bucket that turns into analog equipment, Eurorack is a great thing to pursue. So there's a technique called cross-synthesis feedback, which is super easy on the Eurorack. And what it is you take the output of one oscillator and you plug that output into, I'm going to go out of full screen here so that I can see my mouse. You take the output of one oscillator, the triangle wave here, goes out into the input of the frequency modulation of this oscillator. Now, I'm going to take the output of that oscillator right here and go into the frequency modulation of this oscillator. So this oscillator is affecting this oscillator, and this oscillator is affecting this oscillator. Essentially, we have a feedback situation, and feedback can create all kinds of wonderful chaos, and really, really easily and cheaply, like if you think of CPU, but you get like really complicated sound. So I'll show you that on my Eurorack right here. So why cross feedback? First of all, the sounds are super complex with the simplest possible circuit, right? Just like two wires crossing. The results are super unpredictable, so even the tiniest change of values can result in enormous sonic difference. And then a noise can be like tiny motion in one of the oscillators away from total pitch, and those things are right next to each other. Results are non-linear. Sometimes higher frequencies mean higher sounds, and sometimes they don't. So that non-linearity is something I really enjoy and I want to exploit in digital synthesis. So it leaves us with a system that implies a more intuitive rather than a methodical performance practice, right? Because you can't be methodical with something that is chaotic like this. So here's the code for that in SuperCollider. So I use this programming language called SuperCollider. It is an object-oriented language that was written, the original version was written in 1997, I believe. Second version, 1998, and the third version, which is the current version and is open source, was released in about 2000 by James McCartney, who ran the core audio group at Apple for 20 years after about 2000. So this is what the code looks like. The language itself is a scripting language, but the synthesis engine is compiled. So if you find that interesting, so this is the synthesis of that cross feedback. If I were to draw it out in a graph here, this is what it looks like. And so there's a lot going on basically in this circuit. There's more stuff I'll show you. There's more stuff going on than the simple cross feedback that I showed in the Eurorack. And here's what it is. So I don't know why that happens, but I lose my mouse at some point. So I have this noise. I can control the frequency of that noise. So the arrows are going to be parameters that I can control in the circuit, and the boxes are the things that I am controlling. So I can control the frequency of this noise. I then have a resonant low-pass filter, so a filter that cuts off the highs. I can control the frequency, the amplitude, and the Q, so the resonance of the filter. Then I have a sine wave oscillator, in which I'm sending a frequency and amplitude. And I have a triangle wave oscillator that I'm sending the frequency. To get the cross feedback, I'm feeding the sine wave oscillator into the triangle wave, and then I'm sending the triangle wave back, feeding back into the sine wave oscillator. So that's your cross feedback circuit. So this is the thing that makes sound in the circuit, and then there's more to it. So that output comes out here. I can distort the signal. I can control how much I'm distorting the signal as a argument. And then there's like this dusty on-off thing that can kind of, it's basically turning the signal on and off with amplitude modulation. I can control the attack, release of that, and the speed of it. And then that goes out to another resonant low-pass filter. And that resonant low-pass filter, I am controlling with another filter. So you can see that here's the whole circuit. You can see the whole circuit it's not like the most complex thing in the world, but there's a lot of controls. Basically, I can control, I think it's 16 different parameters to change the sound of the circuit. Now, as a human, controlling 16 parameters at once is actually really hard, right? And we can't really, not even if we could control them, it's difficult for us to process that much information. But I can actually easily process the information of 3 or 4 parameters, right? So this is why I'm using the neural networks, is that I have a joystick which has X, Y, Z, or I have these two X, Y pads, so I have X, Y, X, Y. So 3 or 4 dimensional space that I'm using the neural network to expand out to a 16 or n dimensional space. And you'll see when I show it later that I have some synthesis algorithms that are much higher dimensionality. So I'm sure many of you are familiar with this. I'm using, so I have 4 inputs in this case, and I'm using 3 hidden layers going out to 16 outputs. I'm using a native, I started working in Keras TensorFlow when I was designing this, and then in the meantime, a group at the University of Huddersfield in the UK developed native MLPs in SuperCollider and Max, and yeah, SuperCollider and Max. It's called Flucoma, so you can check that out. They're doing really great work bringing all this stuff to these native computer music languages. So that in and of itself, using the neural net like that is not the most interesting thing in the world. I think the interface is kind of everything, though, and I think that's where things get interesting. So actually, let me just show you the software. Can you see this software now? SuperCollider.
Yes, we can.
Okay, great. So here's the neural net software, or I call them my neural net synths. And what I have that I think is interesting is that, so here I have, I'll just show you. I have one synthesis engine. I'm gonna play it. You can hear those squeaky squawk sounds?
Yes.
Great, thank you. So as you can see, here is all the parameters of that synth, and that's the one I was just showing you. 16 parameters, all of which are going to move in different directions. What I'm using to control it over here are 4 parameters, x, y, and x, y. And so when I move the XY faders around, you can see that these faders move around over here. So what's super cool about that is that, or what I think is really effective musically, is that I can use my controller to actually control 8 different mappings of each synth. So it could be more than that, but I chose to be finite in my choice. So I have a synth, and here's one mapping. Right? And now here's another one. And here's another one. Right, so those are 3, they're all the same synth, and you can see over here that it was moving around all these faders. Now I have that really asynchronous because it's moving graphics can really hog CPU, and my computer was getting old. But you can, those are 3 totally different mappings, but the same synth, so all the same set, all the same synth def in SuperCollider. So in any one synth in this setup, I have 8 different mappings of my neural network, which I can train. Let me just show you this. I'm going to just load these, turn it on. Let's go to this one. Nice and noisy. But if I load the points and 1, 2, 3, 4, 5, 6. So it's really just 6 points on the 2 XY multi-ball controllers that are controlling that mapping, but it's super expressive because I can find this like little area to play around with. So hopefully that makes sense. So each of these synthesizers has 8 different mappings. The cool thing is it's not just one synthesizer, it's actually 4 synthesizers, or as many of these as I want to make. So here's another synthesizer called the noise one. And those are the 8 mappings of the noise one. Here is one, which I think things get interesting. This one's has way more parameters to control. This is actually, if you're a synth nerd, this one uses a model of a DX7, which I don't know how they made the music they made with the DX7, the synthesis model, because it's totally bonkers. But you'll hear that here. So it's a really weird sounding model. There's tons of feedback going on, but I'm controlling so many more parameters with that synth there, and just to show that there's one more. Right. So there's 4 different synths, each with 8 different mappings. So yeah, so one controller can control 8 mappings, and then yeah. So yeah, with 16 different controllable parameters, there are infinite sounds. So this is thinking about a mapping. There's with 16 controllable parameters, there are infinite sounds within the universe of the synth. It's a 16-dimensional space. So even if each dimension only has 100 points, which it doesn't, it has more than that. We have 10 to the 32, 1 trillion to the third different points within that space. So you have to use in order to map that area, the neural net's a great way to do it, because I can't personally visualize that kind of space at all. So there's within each of these synths, because they're actually so chaotic, there's these like glorious little sonic little places, and it's training the network is training to find these little beautiful little sonic gems that I love. And yeah, the obvious solution then is to find multiple mappings and that I really like, and then to be able to quickly and easily access those mappings, which I showed you a second ago. So the software can load 4 different neural net synths, and each one with its own UGen and set of n parameters. And within each neural net synth, there are 32 possible different mappings of up to 4 different synths. So there's just so many different things you can access, so much data that you can access. And I think the goal of any good instrument, think about a violin, is to not just have a lot of data that you can access, but to be able to access that data within a tiny space of movement. And yeah, so here's what I was hopefully showing in the software, is that 4 simultaneous instrument mappings with 8 each, I can quickly move around this space just by moving the joystick or moving the 2 XY pads. Great. So right. So here's some stuff that I think is hopefully interesting to you guys. Feedback systems and neural networks, secret lovers. So what is it that we like about feedback systems? So if you're into music and you're into like no input mixers or audio feedback, or if you're a programmer and you're into feedback systems, they can be really unpredictable and nonlinear. They can have like super simple parameters but have complex outputs. They create this cybernetic feedback system with human users that breeds like this endless play and creativity. So it creates a setup that doesn't really give the same answer every time. It's something that you're really interested in and you want to like keep exploring. What do we like about neural nets? Or what do I like about them? The outputs of the mappings can be nonlinear, resulting in unpredictable sounds. Now, I'm sure many of you are using them for other reasons, but they can be used to map simple parameters onto complex output with a sufficiently complex system, and by intuitive, supervised training rather than direct mapping, they create this cybernetic feedback system where human users can breed endless play and creativity. So these things are really complement one another in how they think. And I think that's why I was drawn to this design. And did I mention cybernetic feedback systems? So one approach to creating expressive instruments using deep learning is to create a training system that is itself a cybernetic loop. So in this case, I want to be able to rapidly train my system. So I want to be able to like find the points that I like, train it, and test it. See if I like it. Reload the points, tweak one of them, take it out, put a new point in, see if that totally changes the result. And so instead of having like a a training set where there's like 1 million points and that's how we're training our network, it's more like a small number of points, just getting them right and then entering the network there. Yeah, and by creating a setup, also in the software design, I can train the network and create the synthesis algorithm at the same time. So they just become this feedback loop between the training and the system, a kind of further feedback loop. And so I think this is really important in musical instrument design, and I'm sure it's really important in any kind of commercial design. So having feedback at all levels of the training. So me as a human, as a performer, I want to be putting information into my audio instrument. My audio instrument itself should have kind of feedback inside of it. And then I want to be getting the sound back to me, and then hearing what's going on, and then sending it back into the instrument and retraining. So yeah, here's some completely unscientific thoughts. And this is just choice of controllers. So I could use a slider, or I could use like just one XY pad, but I actually choose to use the 3 and 4 dimensional controllers, and because I'm performing in this space, the sonic space that I'm performing on, or the instrument that I'm performing on, is this multi-dimensional space, and I can perform in that space and I can hear the differences, but I cannot visualize that space in my mind. I have the same feeling with the 4 dimensions of the 2XY pads. Like I can kind of feel where the sounds are, but like I can't actually understand it. And I think that's actually a good thing in this case, because the number of combinations of up, down, left, right, it kind of boggles the mind, so that I'm actually performing within an intuitive space. And I'm not thinking like, oh, the X value, so if I'm moving the slider from left to right, then that's the frequency. And up and down, well, that's going to control the speed of the modulator. I'm not thinking that at all. I'm just hearing the sound, moving my fingers, and intuitively moving around the space. And that brings up a bigger question, is like, as humans, and I'd love if anyone is a specialist on this, like is sound our way of visualizing multidimensional spaces? Because we're able to hear all these different parameters changing, and we can hear all that stuff, but we can't visualize it with our visual minds, but hearing it is actually no problem. So that's the end of that. And I have another part of the presentation, but I think that I should maybe stop here and get some questions. And then, if there's time for the other thing, great. If there's not, then that's fine too.
Okay, great. So Mark, I think we have some questions. Maybe you can take over.
Right. Oh, you opened me up. Okay, great. All right. One moment. All right. We have a number of questions there. So this is from Jordan. I was wondering if you work with hardware equipment and software which produces tones with a well-defined pitch, basically something which is based on the harmonic sequence in some way.
Yeah, of course. So yeah, that's I have with this instrument, I'm kind of engaging super noisy stuff, but I use pitches all the time. I love beautiful harmonies, but I do think that they engage with maybe different psychologies, and pitches and the way harmonies move. That might deal with a certain kind of kind of traditional emotional space, whereas I would say these kinds of noisy sounds more deals with a brain space of like a focus and awareness, like more of a meditative space, even though it probably doesn't sound meditative, but that for me it is. So yeah, but I love those sounds, of course.
Alexander wants to know, have you experimented with other hardware peripherals? The joystick is intuitively valuable. Are there any others that work well too?
Yeah. So for years I used a controller. I mean, I love the iPad just because it can be super. You can have like so many parameters, and then you can change the visual, which I think is very useful. For years I used a controller called a Snyder Phonics Manta. I'll type that in the I'll type it in the chat. Am I? Yeah, panelists and attendees. So Snyder Phonics Manta. This thing is awesome. And it's like a square controller with a bunch of capacitance-based buttons, but they're not buttons; they're capacitance. So it's how much of your finger is pressing them. And I used that for a long time. Unfortunately, I developed an autoimmune condition where I'm actually allergic to gold, and which is unrelated to the Snyder Phonics Manta, but it was made of gold, and it was actually causing flare-ups of my autoimmune condition. So I've used that. I'm into anything. I'm into any controller. So I've also this software. Let me just share the screen again for a second. If I go here, so the input can be basically anything. So it doesn't, like, I've just given it 4 parameters, but like I can plug in my joystick and map that, and then but one of the other things I've been using, or I used with this is a, why can't I think of the name of it? It's because I'm in front of other people. It's the like hand sensor. What is that called?
Theremin.
No, but it's just like a hand sensor that gives you many dimensions, and I think that leap motion. Thank you, and that worked. Thanks, Ali. That worked. That works really well, and I use it. So that one I used to use the leap motion to control feedback. I have these televisions where I put like 6 microphones on the televisions. This is the biggest network I had, so it's the leap motion. In I don't know how many parameters I was using, probably 4, and then controlling 56 dimensions of this like feedback going into a television. So that's like a really fun use of multiple kind of controllers. But I use joysticks. I have Nintendo Switch controllers, which I've played around with a bit. I think. In the end, we only have sliders and knobs. That's all we have, and buttons, and so any kind of combination of those, I'm down.
Next question is from Jeff Solon. He asks, if you're playing around with the instrument and you stumble across an accidental sound that you love, can you review back through the record to determine what was happening at that point so you can capture and recreate it as assigned to a button?
Right. Yes and no. So it's not the way I've set up the software doesn't really do that. It doesn't really assign it to a button. It's more like assigning a process to a button. So and the process itself is kind of is chaotic. So the sound is going through like many different modules that are changing it. Right, so the sound comes in, maybe it'll get filtered, and then it gets delayed, and then I can loop it into a buffer. But like all of those things would have to line up perfectly for me to perfectly replicate a sound. But what I'll say is one of my favorite things about playing with somebody new is that when we sit down, all of a sudden their world and my world, we start communicating, right? We're communicating. And they will probably do something, if I haven't played with them, they'll probably do something that I've never encountered. And what'll happen is almost quickly, almost within 5 minutes of starting playing, we will create a space that we make music in. And that space can often be a totally new space. And what that does is that allows me, when I'm playing with somebody new especially, like first time playing, it's like I should play with new people all the time because the first time, like they'll do something and I'll find something in my software that I didn't know before. right? So a totally new space that I had no idea existed within the software. And then from that point on, I have that space for for the rest of my life. That was my wife walking by. So that's a super exciting thing. Is like finding a new space within the software. But that's a whole like, I can't really explain. It's not like a button. It's more like a set of settings that I can get to. Yeah.
We have 2 more questions in the queue right now,
Sure.
and we'll hopefully get some more
Yeah.
later, as
Yeah.
you like. This one's from Terry. I find most super colliders, since compositions, etc., works get lost in technology and programming versus musicality. How do you personally overcome this?
Oh man, I know exactly what you mean. So, and I hope I overcome it. That's what we can try to do. I think there's a balance in music technology, because the goal, you know, we all, probably most of the people here find technology beautiful, right? Technology is beautiful. I remember the first time I saw a piece where I saw the code, and a piece of music where I saw the code and I was like, oh my God, this piece is so beautiful. And I hadn't even listened to it yet, right? So that can be we all can probably find attractive and beautiful, and we're all attracted to that. Otherwise, we probably wouldn't be here. But then there's the sonic side, right? And so we want to make something that is musically beautiful as well. And so it's really just playing a balancing act between those two things. And oftentimes, if things start to get too complicated, you're probably doing it wrong, especially with music, because, I mean, I'm making something right now, and I'll tell you, I know it's wrong. But I have to make it to show myself that it's wrong. And I know it's wrong because it's not going to be musically rewarding. And then I'll probably work on it for like literally a month, and then I'll throw it out. So I think that's okay. That's okay. Like, we have to be able to experiment and play around, because the thing that I'm working on is technically beautiful. And so but then I have to double check with the musically beautiful. And if it's not, then it's not worth it. What's beautiful about, or what's exciting about making an instrument like this, I've been working on this instrument, not the neural net stuff, that's just the last year, but I've been working on the larger instrument for like 10, 15 years, right? So, or 12 years, I think. And so it's 12 years of code, and it's 12 years of good ideas and 12 years of bad ideas. And the good ideas stay and the bad ideas go.
And here's the last question for now. This is from John Gibson. If I'm
Hey, John.
memory correct, from Indiana University School of Music. I went there. Sam, I may have missed this, but can you say more about how you are training your system in Super Collider? Is it happening in advance of a performance or during a performance?
No, it's a good question. I do the training ahead of time, and I kind of like, you know, it's a tricky balance, because the what was I saying? Sorry, the synth now has like so many available possibilities that I also need to be sure to not keep retraining it, so I kind of know what it's going to do. So like, once I find a training I like, I keep it, and they're stored. Now I'm working on something right now that basically it's kind of like a live, using these machine listening and machine learning stuff to create almost like a ring modulator. So it's going to be so much work, and I'm just going to end up with a ring modulator, which is like literally like two diodes. But what it does is it takes signal in from a player, and then it listens to their signal over the last like 3 seconds and 10 seconds, and then, or 3 seconds, 5 seconds, 10 seconds, right? Creates 3 different mappings that I can then move between, and it takes their signal and basically turns that space that they created in the last 3 seconds, and turns that into an XY space. So it takes, since there's probably some technical people here, it takes that what they're doing, analyzes it, and then plots it using a PCA graph, so to bring it down to two dimensions. So that creates a 2-dimensional space for them. And so then they're playing, and now the points that they're making that I'm analyzing are then moving around the two-dimensional space. Well, what is that? That's a joystick, right? So it's basically turns their signal into a XY joystick using a PCA, and then uses that to control a synth. So that's something where I'm doing the mapping in real time, but this stuff I'm not. Was there one more, or should I keep going?
Well, we have lots of questions, so you know, let us know what you want to do.
I mean, I'm glad to answer these questions. The other thing could be really short, so.
Okay. There's a question from Mark. Any use of any type of tempo in your performances?
That's a good question. I have. I can definitely play with somebody who's. So most of the time I'm not playing solo, right? I actually play with other musicians, and I play in some jazz bands, and I play. You know, there's drummers, and people are playing in tempo. Now I am almost never. I tend to be this kind of sound mass element in those, or in something moving between effect and orchestration, right? So a string section or something. It's this whole other. It's like another rhythm section, but it's not a rhythm section that is keeping time. Now that is just a choice I've made over the years. I'm not stuck in that, and I'm glad to do something else sometimes and try new things. I think the instrument, the issue with tempo, one of the things is I'm not great like as a counter. So like you would have to be like really triggering things in time. But then the other thing is the instrument, if you're doing processing of sound of somebody else's signal, it's always going to be delayed, right? So the signal is going to come in. Even if the signal comes in and it goes straight out, it's delayed. Because that's the nature of the instrument. That is actually the foundation of the instrument. That's all the instrument can do is make a delay. So basically the instrument comes in, or the sound comes in, and then something happens, and then it comes out. So there's always a delay, which makes it very hard to stay in time with people, because then you're always a little behind. There's always a lag.
Here's another question from Nathan. Could you say a little bit more about how you're training your model? You seem to be implying you had found a quicker, more interactive method as opposed to training off of a large quantity of labeled data at once.
Yeah, so the trainings are not, they're just not, I'm going to share my screen again here. It's just not many, just not many points is the thing. So what I think is, so if I, so, actually let's go, done a lot of noisy stuff. So if I do this one, there's some rhythm. Okay. So if I'm going to load the points that I used to train this. So that's 1 point, 2 points, 3 points, 4 points, 4 points. So the whole thing is 4 points, and it's the 4 points you can see are here and here. So when I load the points, it'll show you where the XY pads are, and it'll show you where this is. And all I'm doing is I find a sound. I move these sliders around until I find a sound that I like, and I go, that's my point. And then I move the XY pads to the point where the lower left corner, or both of them to the lower left, or one to the lower left, one to the lower right, or any combination, and I just say add point. And then I move all these, find a new sound that I think is related in a way or not. Okay, add point. Move these, add point, move these, add point. So there's not many points. There's just 4. I think at most I use like 8. So there's just, and here's the thing, that I'm sure some of you are thinking, well, that's not going to be very accurate. Exactly, it's not accurate at all, and that's fine, because it's it's music, and music actually is best without right answers. Like it's at least I've found that this instrument is best when it doesn't make right answers. It's actually best when it's a random number generator. So hopefully that answers your question.
Okay, Lee wants to know, can you talk about how Flu-Coma is interacting with your instrument?
Yeah, so Flucoma is the machine learning is the network, the neural network. So let me share again, and so I will show you the code for this. I should have had that open. So actually, this is kind of interesting. Is like these are the synths that I've made, and each one, the directory structure kind of stores. So these are different mappings that I've made. So, and it's stored in these JSON files. So if I open, let's see, the NN synth module mod. Yeah. So this one, yeah. So fluid MLP regressor is the object, and I make 8 of them, and that's the instead of using Keras or TensorFlow or pick your poison, that's the object. So I'm not sure those are publicly available yet. So if you've used it, because their listening stuff is available, but I'm not sure if the machine learning stuff is available yet.
Here's 2 more questions.
Yep.
Alexander, again, in working with your neural networks, do you face the black box problem? Is it important to you to know how to interpret what the neural network's learning, perhaps with decision trees?
No, it's actually best that I don't. And this is actually why I love it. I love it because it completely removes that from my thought process and allows me to be musical with the like these 4 things are controlling these 50 things, and I can't possibly like think about the decision tree there, but I can hear exactly whether I like it or not. So it's really just using my ears, and that's why I thought it was awesome. By the way, I'll just say that there's like 3 people to thank for getting into this stuff. One is Rebecca Febrink, and so I don't know if anyone's used the Wekinator, but she's been doing this for 10 years, and she's a real innovator in the field. And I saw her give a talk about this, and I said, because I hadn't seen, people have been using these neural networks in music for a long time, but seeing them used in a live setting was just like, oh, I know what to do with that. And it's to answer your question, it's like I know what to do with it because I knew that I could do something where I didn't have to know exactly what was going on. I also do like knowing what's going on, but kind of creating these like why I love an analog synth. I know what I'm doing step by step, but then in the end, you're like, how did I make this thing? And that's an awesome place to be sonically. And then my grad students, so Ted Moore and Hunter Brown, who are doing great stuff with machine learning, and seeing them do it, it's like, oh, okay, I can make music with this.
We've got a question from Bill. Let me bring that back up here. So where were the synths and neural network actually running? Were they on the iPad or somewhere else?
Right. So the software all runs on my computer. It's basically I'm using the iPad just as a controller, and I'm using the joystick just as a controller, and the synths run on my computer. Now that's a whole other can of worms. Basically, anyone who deals with the audio or deals with audio has a hard time dealing with multiprocessor systems, and it has a hard time because like it has to be super in line. I don't really know the answer to this, but this is my understanding. It has to be super in line, and multiprocessor systems, if you try to line up audio and get them all like sample accurate and they're running over multiple processors, well, a lot of your processing is going to be deal with lining it up. So it's actually very hard to deal with that computational problem. So I've got actually like 10 different audio servers running on my computer, which then are fed back into the computer and run in parallel. So there's a lot of computing going on, but I don't think it would run on an iPad. Also, SuperCollider has a weird license where I don't think you can actually port it to iPad legally.
Okay, Jason wants to know, I totally get why you moved away from Keras. But
Yeah.
let's say that I had an awesome and fast audio generation model trained in TensorFlow's save model format. Would it be possible to use it in a SuperCollider-based system? What steps would someone take to make that happen?
I'm not sure if he means control or audio.
It doesn't say.
So if it's an audio system in TensorFlow or you're doing some kind of synthesis or something, that would probably be really easy. So the way I was communicating with Keras before, it was with Python, is just Open Sound Control. So Open Sound Control is really awesome. It's like MIDI. It sends data between programs. It was from 1998. There's some limitations to it, like you can't send strings or something like that. But you can send like data. So I was basically sending the controller data over to Python, and then Python was sending so I was sending the for controller data over to Python, and the Python would send the end controller back. And so that works really well. So if you're just doing data, then it's actually super easy. It's actually super efficient. In some ways, it's a little better than using it locally because then the Python is running on its own thread, right? So then it's not, you don't have to deal that processing can happen on its own. So I found that aspect of it, I never really had an issue with any kind of processing stuff. Whereas with the local SuperCollider stuff, since it's running on the server, then if there's too much audio going on, it can get a little funky. So yeah, the other way to do it is if you're like doing a synthesis engine or something in Python and you want the audio to come back to SuperCollider, I guess you could send the audio over the network. And if you're doing it in like C, then maybe you could compile it to a unit generator in or C++ in SuperCollider, which the SuperCollider API allows you to create your own unit generators. So if you're programming in C++, you could probably do that.
Okay, here's our last question. It's from Jeff Solon, who I want to mention is one of the teachers of our next month's speaker. Not really a question. This is going to sound a little nutty, but as someone into music, computer science, and speed cubing, Rubik's Cubes, I'd love to see what would happen if you use something like a GAN 356i Smart Cube. It knows every rotation and orientation of the cube. As an additional controller, it uses gyros, accelerators, and Bluetooth. Seems like you could have a lot of fun experimenting with many types and methods of control.
Oh, absolutely. I mean, so you said there's like an accelerometer, there's gyros. It knows where it is. I mean, I mean, you could also like, if you could if you can use that as a controller to like a model that is making certain sounds and say the sounds line up to specific locations within the cube, that could be a really fun way. Now, that would be an amazing way for people with sight disability to learn Rubik's Cubes because you basically have sonified the data environment of the Rubik's Cube. It would be a lot of points. That's the only issue because how many possibilities are there in a Rubik's Cube? My goodness. And it would create this like audio-visual experience of watching somebody control the cube or solve the cube, and I think that would be super cool. That would be super cool. Kind of a intermediate relationship between cube and sound.
Okay, great. That wraps it up for the questions, and we're going to proceed with the rest of the presentation and the closing.
Okay, so yeah, thank you very much, Sam, for that wonderful performance that you've shown, and also for explaining how you go ahead and do that. And thank you all for the questions that everybody posted.
And thank you guys.
So,
those are great questions. Yeah.
Yeah. So before we end, we have our next ACM Chicago webinar, also on the same lines of artistic theme. So I'll play a little bit of what we have in November. Oh, first of all, I need to share my screen. Okay. There we go.
Our next program on November 18th, 2020 is Cinematic Scientific Visualization, where science meets Hollywood visual effects. Our speaker, Kalina Borkiewicz, is a senior research programmer for the Advanced Visualization Lab at the National Center for Supercomputing Applications of the University of Illinois at Urbana-Champaign. Her computer graphics software and tools convert extremely large scientific data sets into high-fidelity, production-quality IMAX screen-ready visuals for documentaries, which have been seen at the Adler Planetarium, IMAX theaters, Hulu, and Amazon Prime. She will talk about how scientific visualization serves a vital role in educating the public by cutting through the noise with meaningful, scientifically validated imagery with high-quality visualizations. Her presentation will explore how scientists, film producers, and education experts work with astronomers, geologists, biologists, and others to create virtual tours of scientific domains for high-resolution, immersive screens which help audiences build a foundational understanding about complex science concepts.
Okay, great. So yeah, we have a great presentation for next month. And if you go to our ACM Chicago meetup, you will find that the page, the event is available there. So you can start registering. I already saw several people already tonight register for that. So yeah, so there was a question regarding about for PDH, professional development hours. Yes, so there will be a certificate that will be sent out, including a copy of the recording and slides from Sam or so. And we can send those out, and then you can put your name in if you need to have a professional development hour certificate. And I'm just going to launch a quick poll here. So we want to get feedback from you, our attendees, right, to see whether these particular webinars, were they relevant for you in terms of how good was the quality, and what are some particular possible topics that you would like to see, so we can be able to cater to our members. Okay, so I'll leave this polling up. And yes, thank you everyone for attending this evening. We had a really great response. I think we had I saw almost approaching 80 attendees, so it's very, very good, especially for in the evening. We're now 7 o'clock in Chicago, so thank you for staying up with us. And so thank you, ACM Chicago. Thank you, IEEE Computer Society Chicago members, and thank you, Mid-America Club members for coming this evening. So that wraps up for tonight. Thank you again, Sam, again. And
thank you, Sam.
Thank you, guys.
We'll see you in our we'll see you in our next talk in November the 18th.
Thank you, Alban. Thanks.
Thanks, Sam.
Bye-bye.
Okay, and then bye-bye.
Yeah, I think that worked pretty well.
Yep. let me just stop the recording.
We definitely got a lot of questions.